Is it recording now or? Okay. I didn't get any notification or anything. Okay, looks like we have 30 people now. I guess we could start. So thank you everyone for joining. Good morning or evening, wherever you are. Um, Here's the plan for today. I'm going to give some very brief tedana updates just so you're all in the loop with a couple of the latest releases we've made and the things you can do now with tedana. And then we'll have three really, really cool presentations. The first one will be about how you can use external regressors to help with the classification that tedana does. Then we will have another one on multi-echo denoising for EPTI. And finally, we'll have a talk on how to use fMRI prep in combination with tedana. And at the end, we'll have an open Q&A session discussion, so you can think about what you want to ask, what you want to ask us, and yeah. So without further ado, I just wanted to highlight two of our latest releases. This one is from 2 years ago, where we introduced a way to create your own recipe in tedana. So this is with the tree option. You can give it your decision tree. It's what we're calling it, but your own recipe to tell tedana how it should be classifying components, which means you can also share it once you publish your paper, right? You can share your recipe so your work can be reproduced. And at the same time, if you happen to manually classify components, then we now have to use this ICA reclassify. So if you're using RECA, for instance, this is now the way to reclassify. And finally, there are no more components classified as ignored. It's either accepted or rejected. And then last year, we made this, I think, very big release that allows you to finally include external regressors in tedana, which can now be used to classify these components. And hopefully that helps you, keep your task-related regressors in your classification, for instance. And at the same time, on that same release, we added this robust ICA option, which should give you more robust components. So basically, it's running ICA a bunch of times and then trying to find what components are stable across all those 5-10 runs, and it only gives you those. So I hope that we hope that all these changes help you with your multi-echo data analysis. Now, if you have any code-specific question or comment, you can open an issue on our GitHub. But generally, what people do and what we ask people to do is to ask the community on Eurostars. A few of us monitor the space, so you just have to use the tag tedana or multi-echo. We will probably get an email and try to help you. And then just so you know, if you have a very specific case that is not covered by any of those two, or you want to talk to us directly, joining one of our developer calls is probably the best way to do it. And just a call to welcome anyone who is happy to contribute. We welcome all sorts of contributions. It could be code related, but it could also be documentation, tutorials, sharing your workflow so that other people can learn how you're doing things. This is all very welcome. So just put in touch with us and yeah, we'll be happy to have you in the team. Now I'll pass it on to Neha, Sarah, and Michelle, who will talk to us about external regressors.
All right, let me share my screen. All right, can everyone see this? Yeah? All right. Okay, well, thanks for the introduction. Today I'll be talking about some early experiences that we had combining head motion and physiological measures with multi-echo diagnosing. My name is Michelle Medina, and I worked with Neha Reddy and Sarah Goodall. So as a general outline, I'll be mentioning some current challenges for multi-echo ICA data, specifically with task-based fMRI data. Then mention some limitations of the current strategies that are in place. Then I'll talk about the implementation of decision trees with external regressors. I'll mention some testing overviews and finally some conclusions and next steps. So I want to start off by saying that tedana has multiple decision trees that are available now, but one that's very commonly used is called the minimal tree, which is shown here. And as a refresher, this tree is just very popular given that it's very easy to understand and it has less stringent thresholds on the rho and kappa components. These rho and kappa components are used along different nodes in the tree to be able to classify the components as either related to the bolt signal or noise. And so I just wanted to have everyone be aware that I'll be using this component for comparisons in the presentation. So starting off, I wanted to show that the existing decision tree works well for certain components of task data. I'm presenting data that was taken using a passive auditory task. And this is an example of a component that was accepted by the original decision tree in tedana. And it's really not surprising why. If you look at the spatial maps, there's high signal in levels of expected activation. This is the primary auditory cortex. Then looking at the time series, we see this periodic structure that's very analogous to this like block design that we use for what the task regressor time series looks like. Now moving on to the power spectrum, you see a very clear peak, which is about the frequency of the task. And then if you look at the rho and kappa, you kind of have a perfect example of low rho, high kappa. So for this component, the decision tree worked really well. Now, moving on to other components, the classification may become a little bit more challenging. This original decision tree decided to accept the component, but for certain things that I'll be talking about, I personally perhaps wouldn't fully agree with the automatic classification. If you look at the spatial map, you see this artifact, which is like striping of negative and positive signal, which is most likely related to noise and not bold. If you look at the time series or the power spectrum, you don't see the same consistent patterns that we saw on the other components. It's kind of all over the place. And although you do have a relatively low rho, you also have a relatively low kappa. So it becomes a little bit harder to say if this component should be accepted or not. And lastly, I wanted to show a component that the original decision tree decided to reject. Like I said, this is not truly surprising. You still see that same striping pattern in the spatial maps, which is most likely noise. But interestingly enough, if you look at the time series, this is the time series of our task regressor. And in the power spectrum, you still see that clear peak, meaning that this component must be related to task, and we wouldn't be wanting to remove this signal. But overall, like there's just some ambiguity in the classification of this particular component. So as a temporary solution, a lot of people have started manually classifying the components, and it has multiple advantages. Classification rules are easily to adapt to each particular study. You can follow a set criteria that involve characterization using the provided information, like the time series or the power spectra, like I was walking through some examples before. However, manually classifying the components is very time consuming, especially if you're needing to classify like hundreds of components, especially if the data, there's a lot of motion. It is somewhat subjective and it's really hard to reproduce even within labs, just because people tend to value specific parts of the characterizations more than other parts. And it also requires training. And even then, like I showed you, some components have very ambiguous classification. And so it's hard to know if your manual classification is truly like as perfect as it can be. Recently though, like Aneka was saying, tedana has come up with some really helpful and new capabilities. users are now able to create their own decision trees or even use some that Tedana has provided in their documentation as examples, such as the one that I'm presenting here. This decision tree is able to incorporate external regressors and use them as part of the component classification pipeline. For instance, if a component were to be correlated to a nuisance regressor, such as a motion parameter or a CSF regressor, then this decision tree would reject this component. And there's also the option to incorporate a task regressor. And if the component were to fit the task, then the component would get accepted, regardless if it was provisionally rejected due to fitting a nuisance regressor. So this decision tree is currently being tested, and I'll just provide some observations of things we've done with this decision tree. So to start off, I'll present some just component classification examples, but comparing it within 3 trees. First, the minimal tree that I presented before, then this nuisance or external regressors tree, and then that nuisance tree, but including the task. So starting off with like a very clear example of a component that presents no clear periodicity in its time series and no clear power spectrum peak, and also no activation in expected area. So all the decision trees ended up rejecting this component. Moving on to this one, although you do see a peak under the 0.1 hertz frequency that we would want for a component that we would want to accept, this component actually was correlated to motion in its time series, which is why it was rejected by both the nuisance tree and the nuisance task tree. I do want to point out that the minimal tree still accepted this component, so something to keep in mind. And then for the last component, you see this pattern that we kind of are expecting of looking like our task regressor and some peaks under and along the frequency that we expect for the frequency of the task, and some activation in this like motor area. This was actually a hand grasp task. And so upon further investigation, we saw that this task was correlated to both the motion regressor, which is why it was rejected by the nuisance tree, but it was also correlated to the task, which is why the nuisance task tree ended up accepting this component. So I'm not saying that one tree is like the perfect way to go about it. Just to keep in mind that you have to decide based on the purposes of your study, and you may be valuing something more than something else. And so this is why being able to create your own decision tree or even using one that kind of fits what you want the study to be focusing on can be extremely helpful. Now, Molly Bright's lab has actually tested the external regressors nuisance tree on multiple motor task datasets, and we were able to compare it to a lab standard of manual classification. Overall, the result is that the external regressor classification ended up rejecting fewer components, meaning that it's a less aggressive denoising. But even though it's keeping more components than we kind of rejected in our manual classification, the conclusion was still that there was no harm done. And I'm going to show this on some beta coefficient subject level maps on this next slide. First, I'm presenting a low motion subject. And on the left, you see the beta coefficient map while using the manual classification, and on the right, the automatic classification with the external regressors. The arrows just point at regions of activation that we expect in the primary auditory cortex, since this particular data is from the auditory task. And if you can see, there's just very high agreement between the manually classified and the automatically classified maps. And maybe to have it be more convincing, I also included a high motion subject. And we kind of see that same story of like expected regions of activation, high agreement between both maps. And this just solidifies that conclusion of no harm done when doing the automatic classification. Obviously, there's still more testing that needs to be done, but these are just some observations that we've had. So to conclude, the external regressor decision tree is very promising for task datasets, whether it be with like the low or the high motion. And as next steps, more testing is needed to be able to determine optimal values, given that the current regressor thresholds are somewhat arbitrary in terms of like the R squared and p-value. So yeah, thank you so much for listening, and thank you for coming to this meeting.
Thank you, Michelle. Does anyone have any questions? I think we have a couple minutes.
Yes,
Sorry.
sorry.
Oh, you go ahead.
No, please. I will ask after you. Thanks.
Oh, okay. Yeah, Michelle, great presentation. And for somebody who uses Tedana with task-based stuff, it's very, very exciting to see these developments. One thing I'm curious about, so now with the nuisance regressors potentially being included and then the task-based regressors, of course, is there any possibility that there would be any kind of inclusion of, say, the other types of um, signal versus noise metrics that are included in things like ICA aroma, for example, edge fraction, and kind of like merging edge fraction, like percentage of voxels that are within the edges of the brain mask to also be included as well. I know that's kind of a different field entirely, and you already are doing such amazing and hard work, but I'm just curious about if there's any future steps like that.
Perhaps I can't speak if that's like kind of in the works, so I see that Dan kind of unmuted himself, so.
I could mention that the functionality is all there. So the one little quirk is you have to give it the time series yourself. So like if you want it is now, I know some other people are actually working on this, but if you wanted to make a time series of your CSF, a time series of your edge fraction, and all these other time series, you can put it in and fully replicate a merged IC aroma and tedana method within the code right now.
Nice.
There's work to it, but it's 100% possible. And if anyone wants to do that, I can absolutely connect you with other people who are also working on this on the same thing. But that is a definitive feature that we're trying to add.
Thank you. That's very exciting to hear.
And my question was, maybe I missed it. The CSF external regressor, is it the ROI you choose in the brain, or what is it?
So for this one, I think it kind of depends on your purposes. Like you can make an ROI and then extract the CSF regressor from that. But for the examples that I'm giving, it's just like the average CSF of the brain.
Oh, the average signal. I see. Okay. And would you be what would you think if we add other external signals like respiration, like if we have respiratory belt signals, what would it add to your analysis, or would it be necessary or not redundant if we add this as a regressor?
I'd say that it depends on like your study. Like for example, it could be beneficial to have that. And I think that you could probably just check the correlations between regressors so that you don't need, in case like to test for redundancy. Like it could be really helpful or not. So
But I thank you again because you gave examples with the ICA components one by one. I like seeing those motion-related lines and the noisy, because you have to look into your data, all the components to see what is going on, right?
yeah, exactly.
Thank you.
If you have any more questions, we can continue during the Q&A session. The floor is yours now, Katie.
All right. Hi, everyone. Can everyone hear me? Yeah. Yeah, cool. So my name is Katie Lamar, and today I'll be covering some of the updates I've made to Tedana to make it compatible with data acquired using echoplanar time-resolved imaging, or EPTI. So I don't know if any of you have heard of what EPTI is, but basically it's a variant of EPI introduced in about 2019. It was designed to minimize the distortion and blurring artifacts that we see with EPI without sacrificing the speed. It's able to do this by essentially highly undersampling the KYT space. So I have a little animation here of kind of how it works, but basically then the top right plot is the KYT, and then you have your KY, KX on the bottom two plots. And you can see how it undersamples in KY and in time, but it does it over and over and over again. And it's going to use that along with the the spatiotemporal relationship of what we know how we know the signal generation occurs, and from that is able to learn the pieces that it misses. So essentially, by undersampling, we can recover these missing points by exploiting the correlation across time and the phase and coast directions. And so how does this work? Well, it uses a subspace reconstruction, and I'll kind of give an overview of what that is. I mainly want to focus on what I did to tedana to make it work with ePTI. So I'm really going to talk about the parts that are more important for that, but happy to answer more questions about the recon as well. But essentially what happens is this. Suppose we have this signal evolution, like a T2 star decay that you see here. What we can see is that, all these voxels kind of have something, similar over time. They have the same kind of looking decay curve, right? And because they're highly correlated, we can represent these time series using a very small basis. So we can create a basis by just varying T2 star values or whatever type of signal you're looking for. And from that, we can take the SVG. And what we'll notice is that it's a low rank matrix, as you see here. So we don't need all of the components in order to represent, our data, at least, not to represent accurately. And so what we do is we grab maybe the first 4 components here, or, some other, like maybe the first 3. And from that, we can represent our entire data, our entire time series that way. So now what you can see here is we'll be able to take our data and represent it as the PCA represent it as a combination of the principal components here. So X is like my data. The phi here, that's the principal components, and the alpha are the coefficient maps. And from that, I can construct the temporal dynamics. So how does ePTI use this? Well, basically, it just is going to minimize this the error here. So what it's trying to do is it's trying to figure out what those coefficient maps are. So it's severely undersampled, but because we know what the relationship should look like over time for these voxels, we can be able to kind of pick out the points or learn the points that we missed. And that's essentially what it's doing. So now we can, speed up the acquisition and thus also minimize a lot of the distortion that we're seeing due to it taking more time. And so from that, we end up getting a lot more echoes. For my data, I can end up getting 122 echoes or something very big. But tedana isn't quite designed for that in mind. So essentially what you'll notice is tedana has this F statistic that's calculated in order to get the rho and the kappa values. And that's usually it's usually multiplied by the number of echoes, because that's the degree of freedom, or the number of echoes minus 1. But our degree of freedom was reduced, right? Because when we took we did the subspace reconstruction, we only grabbed 3 components or 4 components. And so in order for tedana to work, we had to change the degree of freedom. Otherwise, a lot of the values were just really high. And now the decision tree got all confused, basically. So it was all scaled up. So that was the first change that we made. And this allows us to actually use the decision tree that tedana has. Otherwise, basically all of our task components got rejected immediately. But then we also had the question, can we do more because we have more echoes? And basically the answer is, I think so. So we wanted to take advantage of the fact that we had so many echoes, and we did so by essentially kind of redesigning the way tedana determines, the kappa and rho values. So usually tedana splits our model into a bold changes, like a model that describes bold changes, which is the R2 star model here, and a model that describes signal changes that are not bold related. And we split it because we don't have enough echoes in order to make to actually have an accurate output of our fit. So instead, we split it into 2, like I said, but now that we have more echoes, we can actually keep that full model. So for the work that I've been doing lately is, can we have maybe a better representation of kappa and rho using the full model, the F statistics using the full model versus the reduced model. And so I'm going to show a little bit of my results from that. All right. So just a little bit about the experimental setup. I have the scan parameters here. Basically, it was just this nice, simple tapping exercise, 30 seconds on, 30 seconds off, tapping on one side of the, on one side only. And then for the pre-processing pipeline, we ran it through fMRI prep, and then of course through Tedana, with the changes to the degree of freedom as well. All right. And so here are some of the results that we got for this one subject. Actually, since then, we've acquired 5 subjects, but I'll mainly just be showing one. But the results are staying consistent with it. So here's just one slice of that contains some of the the activation that we see. So on this left side, I have the component that looks most like our bold signal. It was accepted, which is good. And then we compared both the full and the reduced model. So the reduced model is what we usually use for Tedana by splitting in both a bold related change model and a non-bold related change model. And then the full model is the one put together. And a couple of things that we started to notice is that for the full model, we have F-statistic maps that have more dense clustering where we have activation. So there's more uniformity there rather than with the reduced model. It's kind of like some high values followed by some low values and a little bit like that. And we matched this to the time series to actually see, is this where the bold was occurring? And it was. So the F-stat is doing its job. And then over on the lower right-hand side, I have basically included a plot with the full model on the y-axis and the reduced model on the x-axis, which is basically comparing the T2 f-stats of both of them. And what we can notice here is that the t-stat is greater than 0, which shows that the average mean, like the average of all the f-stat values for the T2 f-stat values that we calculated were higher for the full model than the reduced model. So it's basically saying, it's more bold related than maybe the reduced model had originally predicted, which is another, thumbs up for maybe using the full model if possible. And then next, we wanted to continue to see what this started to look like. So we did 2 more. We did the same EPTI tap kind of experiments, but we also did a like a rest experiment. So there was no task. And basically what we saw overall was that actually if we're just looking at the kappa and the row values, there is like it seems that the reduced model actually overshoots for a lot of the values. That basically says that it's more likely, it has a higher kappa than the full model originally predicted. Whereas, and same for the row as well. So this kind of says that maybe the reduced model is giving higher, or saying it's a better fit to both than it actually is. So that's kind of some of the things we're seeing. And then how does this matter for the actual classification? Well, some of those noisy components that have been accepted using the reduced model are now being rejected by the full model, which is kind of interesting to see. I didn't include it here, but it was being rejected by the second node of the original Tedana tree, which is also the second node for the minimal tree as well. And it's basically saying that the number of noisy or non-bold related changes are higher than the number of bold related changes, and that's why it would be getting rejected. But in the reduced model, it's actually saying the opposite. So we think that this might mean that perhaps the full model is better able to pick out the noise related changes better than maybe the reduced model is, and maybe give us more accurate decision making in the future. So that's where we are right now. We still have a ways to go, but yeah, we're very excited about using all there is with Tedana with EPTI. So yeah, does anyone have any questions?
That was really awesome work. That's super cool. I remember seeing EPTI a while ago, and I was just waiting for someone to do something with Tedana with it. Do you have any feeling from when you mess with the data with how many echoes you need to use the full model? I mean, do you think you need 100, or is that like an overshoot? I'm imagining like some sort of asymptote, right?
Yeah, so I don't think we need 100. I actually think that far less echoes are probably even needed for ePTI in general. I think we just kind of started with, the number that was recommended by MGH. Didn't want to mess with it too much, but we have tried a little bit like 3 and 5, and that wasn't quite, with just the regular multi-echo API, and it wasn't really working. I kind of get like weird results, sometimes fine results for other data sets. So it's kind of, I'm not sure if there's a great way of testing to find the optimal number that you need in order to use this method. I'm sure that's, maybe Dan has, or one of these other guys has a good idea on how we can maybe do that. But definitely probably more than what multi-echo can necessarily provide. You might need something more like ePTI to do it. So
yeah, I was imagining writing the EPI echoes. So instead of putting in 100, select every third echo and see. And at some point the F-stats will go back to favoring the reduced model.
Yeah, we tried every other, so odd. We tried every 3, and all of those worked, or didn't have very much.
So 30 is kind of our floor right now, where
but we could probably keep going, but then
we
also have the question on which ones do I choose? Because I can just do like every 3 or every 5, but maybe, maybe if I picked, more highly dense around the 30 millisecond mark for the TEs, then it gets kind of, I need a better way of sorting and finding, because it also is going to be a little dependent on that.
Right.
Yeah.
Cool work though. Thanks.
I think we're going to have to move on with Brandon. If you have any other questions for Katie, you can ask them later at the Q&A.
Sure. And so I'll share my screen, and Echo, let me know if you want me to send the slides to you, whatever way would be best.
You can share your screen now.
I'll share.
But you can definitely, if you send us a link to your slides, we can send that with the newsletter as well.
Yeah. Afterwards, but for now, I'll just share my screen. Yep. Okay. Can you see the screen?
Yes.
Okay, perfect. So yeah, this is going to be kind of a sort of double-edged talk. I'm first going to briefly talk about some of the work that I've been doing with fMRI prep bridging to tedana. Maybe some of it is self-evident, but some stuff I thought might be useful. And then a little bit about the work that myself and Todd Woodward, who's also on this call, have been doing with validating multi-echo task data using constraint principal component analysis. So, and I'm a PhD student at UBC, for way of introduction. So we just of course talked about scripting from fMRI prep to tedana with the last presentation. But of course, fMRI prep is this useful standardized way of pre-processing fMRI data. And I have done some work in trying to see how we can best get integrated with tedana, building on the excellent scripts that have already been provided by you, the tedana team. And currently fMRI prep, of course, already incorporates tedana to run optimal combination at an early stage using the curve fit algorithm. And normally this optimally combined data is carried forward for other pre-processing steps. However, if we're wanting to do ICA using tedana, we want, my understanding is we want to have each echo pre-processed individually, and then the optimal combination ends up happening in pure tedana after fMRI prep is finished. So I use the option ME output echoes to individually preprocess each echo through fMRI prep for import into tedana. Now, to use these echoes in tedana, I'm working from Julio Peraza's script, and I am obtaining these preprocessed fMRI files for each echo. So kind of just in a list format here for examples of code. I read the echo time from the corresponding JSON sidecar.
We can't see your slide.
Oh, when did the last one disappear? Is it frozen or something?
I can see them.
First
Yeah, I
title
can see
was
them.
there, but I can't see I can't see anything.
I think that might be on your side, I'm afraid.
That might be just
Oh, sorry. I might have clicked something. Sorry. Okay.
Yeah.
Thanks.
Okay.
Sorry.
Yeah. So I'm just on slide 5 here. So yeah, for each echo file, read the echo time from the corresponding JSON sidecar. So again, some script that I use for that. realized that it was very important for me to sort the echo times. I think in the initial version of the script, I didn't know if it was automatically sorting the echo times, and that was causing some problems. So important to sort those using the Python command relevant to that. And then I found it was relatively straightforward using that script to pack up the nifty and JSON files together into a zipped format, like so, to package everything together and send it over for the preprocessing using the tedana workflow functionality. And within our group at UBC, we have had some discussions as we were trying to determine, which of these options are the best to use. So, I mean, like afterwards, I'd be happy to have a very brief discussion, if we can, like confirming whether the curvilinear fit is still the best type of fit to use. And then for the TED-PCA method, whether the Akaika's information criterion is still the best criterion to use. And I know that there's also a lot of work being done, as we've seen today, on the decision trees, which is very exciting. And so far, we haven't been doing the global signal regression at this point, so we've got GS control as none. And then afterwards, I have been warping things to standard space using ants, although I've also been trying FSL with fnert and flirt, and I've had relatively good results with both. And this involves pulling files from fMRI prep actually for the T1 weighted to MNI transform file, and using a bold reference volume from fMRI prep, taking the denoised bold from tedana as an input and warping it quite robustly and non-linearly into standard space. So that's the first part of the presentation, super quick there. And now, Todd, I hope I get this part right. I want to talk a little bit about how we've been investigating signal to noise ratio in multi-echo in task-based situations. So here at UBC, we've had a working memory paradigm used by Todd Woodward's group to validate the quality of data at each echo on a couple of different scanners. So using a process called CPCA, which I'll briefly describe, we were looking at canonical networks of brain coactivation that are expected at different stages during the task. And they examined the extent to which each network would manifest as expected or not. Thank you for the link, Todd. Yeah, that's going to be very helpful as well. And so the idea is that we have these predictable bold activations, predictable hemodynamic responses coming at different times, after a stimulus during the task, that we can see if we can recover at each echo during a multi-echo task. So that's how the task looked. It was a memory task with an easier low load condition on the left and a harder high load condition on the right, where you had to encode either fewer or more letters on screen, engaging different levels of cognitive effort demands. And again, don't want to spend too much time at the task, but there were different levels of delay and different numbers of letters that had to be encoded, maintained in memory, and then retrieved shortly after over the course of 56 trials, so 10 minutes per run. So just to get kind of this really canonical working memory / response process. And so they hypothesized that over a longer delay period, there would be a deactivation of a specific response network, a dip in the hemodynamic response, kind of on average, if you will, whereas the shape of the cognitive load condition would stay the same, regardless if it was easier or harder on the hemodynamic response shape. And there would be different times of onset corresponding to the response processes. So again, these canonical hemodynamic responses expected. And the idea was to determine the effects of single versus multi-echo sequences on the quality of fMRI data and results, and look at the effects of a scanner upgrade that was recently done on these results, and develop a technique that is specific to task-based fMRI for quantifying the quality of fMRI data. So again, in brief, we calculated the anatomical Z-scores, which is a way of being able to classify what kinds of networks are appearing at different points during the task using the classification algorithm. And these networks often ended up including, a motor response network for also auditory networks and just general attentional networks that were at play when people were attending to the task. Happy to discuss this more afterwards, of course. And then also there was a temporal Z-score method that was used, just kind of a repeated measure ANOVA that was used to calculate and evaluate the extent to which these networks were recapitulated both spatially and temporally in the brain, and obtain a Z-score, which is a score of quality in this case of the network appearing. And then, most crucially, we were using fMRI CPCA, which is a way of doing constraint principal components analysis, briefly shown here, a kind of special regression model that has been developed here at UBC and University of Victoria, which allows us to do a finite impulse response model weighted according to the various stimuli and expected responses that are shown in the task, and allows us to evaluate components which spatially would look like networks that we are evaluating with the Z-score, and temporally allow us to plot out the expected hemodynamic response for each of those networks, showing the degree to which those networks are co-activating and working over time. So then we were able to calculate temporal signal to noise ratio. We found some somewhat surprising results maybe of shifts before and after a scanner coil upgrade, in which there appeared to be potentially like a lower signal to noise ratio in some brain areas after a scanner upgrade. In the case of each of these multi-echo sequences, and especially after the combined echoes, actually almost at a glance appears to be a lower signal to noise ratio. So a lot of stuff we're trying to investigate and debug with our scanner sequences, but in a way that's a little bit easier to interpret here. What we observed is that while you might expect the first echo, what you're seeing here is having the highest signal to noise ratio, which I guess is the property of the early echoes, as you might see, when you're looking at your multi-echo denoising. But what was interesting to note here was that actually also the first echo had the worst recovery of the networks, of these canonical networks associated with the working memory task. So maybe that's to be expected, because there, while there's a high, signal to noise ratio, the bold activation has not maybe peaked. Is still, while it already has been peaking, this is not being picked up effectively in the first echo, but the second echo and to some extent the third echo are effectively retrieving and showing these networks that are associated with this working memory task. And then at the combined multi-echo, we actually find that we're getting some performance that is at least similar to, but sometimes actually worse than, single echo performance. So all this to say, really what we're seeing here, and we're still trying to investigate this, very much a work in progress, that it's not always the case that this multi-echo combination is going to give us like necessarily better. It might give us better signal to noise ratio, but it's not always going to give us better recovery on task-based parameters. It's not going to give us better recovery of networks of activation that we expect to see in tasks. And that's just kind of a summary of what we see there, with E1 always being the weakest, and E2, second echo combined being fairly equal, and the third echo usually being a bit higher as well. And then we're kind of doing some more analyses on these data which have been denoised using tedana, and because to begin with we were just looking at optimally combined data, but we also wanted to look at this to see if using tedana, of course, is going to improve these results more effectively. And we're also comparing some different processing pipelines like fMRI prep and SPM. So all this to say, we are trying to figure out ways to do effective, evaluations of task-based fMRI at each individual echo, and seeing how that looks before and after we do denoising. I think some of the tools that have been shared today that people like Michelle are working on are also going to be very useful for that as well. So I know that was a bit of a whirlwind, just wanted to get that information out. But thank you to Dr. Todd Woodward, who's here in the call, Dr. Vesna Sosi, and everyone else who's helped with this project here at UBC. Yeah, I'm happy to answer any questions.
There are no questions. I will ask. Brandon, are you planning to make your fMRI prep tedana scripts available for the community?
I'm more than happy to. So what I will say is that it's a relatively light modification. The main script is a light modification of the one that's already available on the Tedana website, but I'm absolutely happy to make that available as something that I have tested and worked through a bit and has some modifications. And also I'm happy to provide my follow-up ANTs normalization scripts that are specifically tailored to an fMRI prep / Tedana pipeline. If people would find those useful, just let me know where would be the best place to contribute to those, like on GitHub or through some other list or whatnot.
Yeah, I think you could just share a GitHub repository with us and we can add it to the documentation. But
Sure.
yeah, that's one of the questions we often get on Neurostars, like how can I use fMRI prep and Tedana together? So the more scripts that we have available for the community, I think I will be for the better.
Yeah, absolutely, for sure.
Hi, I have a
Thank you.
question.
Sure.
Thank you for the talk, and I'm also trying to use fMRI prep and then go on the test data. Did you by any chance compare the signal to noise ratio and the task effects besides the connectivity?
What do you mean by the size of the effects?
Yes, like the task effect sizes.
Let me take a look here. I don't know if I have any specific slides on those. I do have some more slides which look at individual networks. Todd, I'm not sure. Was that something that you looked at as well? I'm not sure if that was in the main presentation that you were looking at. If you're still on the call, Todd.
Yeah, I'm still here. Thank you. Yeah, it's hard to explain quickly, but the Z scores that Brandon mentioned actually are effect sizes for the task. It's just that it's not functional connectivity the way you're used to thinking about it. It's not parcellation correlation matrix. It's a combination of multiple regression and principal component analysis that ends up with the bold signal that is induced by the task being retrieved by the analysis, and then the effect size is computed by the magnitude of the bold change. So it's a lot to explain in a few seconds. I sent a link that has a lot of background, but it's just a different way of doing task-based analyses.
Yeah, thank you so much for clarifying.
Okay, sure.
Okay, I guess we can move on to the Q&A then, the general discussion. Sorry, Dan, I see you're writing on the chat.
Yeah, I just left something in the chat so everyone can see this, but we wanted to make sure to leave some time at the end because this is the first time we've done this. If people have more questions specific to the talk, that's welcome. But we're also looking for, if you have more just sort of open questions on multi-echo or Tedana, that's welcome. Either raise your hand or type. And lastly, like I said, it's the first time we've done this. I think this feels like it's gone well, and we'd like to do more, but we want to know, what are people interested in? Like, we kind of crammed 3 talks in here. Do we want more informal, more discussion, more, similar format, all that stuff. So feel free to chime in.
I want to actually say something that after this fMRI prep output, echoes were collected separately. Like you can tell fMRI prep. Of course, maybe Dan may not be happy with talking about this when there's fMRI there, right? But anyway, so since this is opening up, there is another thing that I used like XCPTD software, and it just, I wonder your Brandon's thing can be also implemented in there because it's also open software and they can use Tedana to use these echoes to fit, like mine was just 3 echoes, but it worked like this CPDD software. I don't know if anybody used it, but it gives nice reports too. Like, I don't know, like, or fMRI, whatever, like it can be, what do you think? Anybody use that software?
You're saying XCPD?
Yeah, XTP-D.
Yeah, I'm the maintainer, and I'm
Oh, you
also
are
Oh,
okay.
nice.
I'm also
Okay,
a
okay.
Tedana maintainer. Yeah, so I will say that you can take Tedana outputs and organize them into a BIDS-like structure, and then feed that into XTPD as a nuisance regressor set for denoising. It requires a little extra work though at the moment. My goal in the long run is to create a fMRI post Tedana, which would be a NIPost workflow, like a BIDS app for post-processing, additional post-processing on pre-processing derivatives that would then create an actual BIDS data set to make it easier to combine Tedana outputs with other things and run them on, or run XCPD on them. But right now that's on a wish list, not really in practice.
So basically, when we run say called XP on fMRI prep output, it is already doing Tedana automatically, right? Because the bits, but the bits JSON files describes the echoes are designed like the say. So what does it do then? Like
What does XCPD do?
yeah, like when there are multiple echoes for like it gives output of. I thought it is doing Tedana.
No, what it does, so fMRI prep will run the optimal combination step, and then XCPD will grab the optimally combined data in a standard space, MNI 152 NLIN 6, 2009 C ASIM, or FSLR, or MNI
Okay.
Infin.
Okay, so
Uh,
fMRI prep does that part. Okay.
yeah, and it does further denoising on those data in the standard space, but it can use regressors from Tedana if those are provided in the right organization. It can also use regressors from Aroma or, in the long run, other things. But yeah, it doesn't actually run Tedana internally. That needs to be done separately and then fed into XCPD essentially.
Got it. Okay. Okay. Great. Thank you for clarifying.
And if I could just add to that very briefly, for AFNI, I have used actually like from a long time ago, even MEICA with AFNI because it was all, wrapped in together. But I know that now, of course, like we're at the stage of Tedana and it's kind of become its own thing outside of AFNI. But I think that the two software go quite far back, needless to say. So I think that you could very easily integrate into an AFNI pipeline as well. And I've had some experience with that too.
Sure, if I can weigh in on that a little bit, I would wholeheartedly agree. We have a lot of examples published using it. So in part it's helped a lot because some Tedana developers happen to be down the hallway from us, so we have a lot of ongoing discussions. But yeah, we have a lot of examples using it, and the older Mica is kind of still there, mostly for comparisons as Tedana was being developed in that. But yeah, most we just recommend that people use the newer Tedana now, and it's we have instructions for pip installing Tedana and including it in like Conda install environments along with AFNI when it's set up as well. So yeah,
That's fantastic.
yep, it's nice.
Paul is the director of the AFNI team. And I'll mention that the developers of Tedana have close connections with Paul and the AFNI team and some of the people on the fMRI prep team, which is why there's a bit better integration. If anyone here uses other packages and wants to make better connections, I think the idea of Tedana is it kind of is designed to be slotted into other things, but the other people have to make the slot. So if you want in other packages and feel free, or if you're developing other packages, we are welcome to figuring out how to make things work. But those are the two packages that currently the developers have been extremely, welcoming and active and can make connections.
Any other questions or comments?
Usually, oh, sorry, you go ahead.
I just wanted to speak to combining Tedana and Aroma specifically, since that came up. That's something I'm actively working on now. It is not an easy thing. In mostly because aroma is so fragile. And I don't mean it, I mean that it requires specific data in a specific space and resolution, and with a specific smoothing with Susan. And we actually had a hackathon at a Tedana hackathon at NIH several years back. We tried very hard to implement aroma in native space so it would work nicely with Tedana. It did not go well. So right now I'm pursuing something where I use the mixing matrix from aroma, which has to be in the specific space, specific denoising, etc., and feeding that into Tedana. So that's not really, while you could do something aroma-like with Tedana as it is, you cannot do like aroma proper. And so just be wary of, like, you might think the hyperplane classification would apply well if you have, different, native space masks instead of the standard space ones provided by the aroma team. No, it will not produce something similar. So just be aware of that.
I'll just add, I think it's very possible to replicate aroma as the algorithm was published in their manuscript. It is very hard to replicate the exact outputs that you would get from aroma without using their code. And I say that as someone who ported the MICA algorithm into Tedana and tried to make it replicate. I am not doing that again. It is extremely hard to sort of replicate precise steps that someone else made in different code.
If anyone's really interested in it, I'll make some code available as soon as I get it fully working. I used fMRI post aroma and fed the mixing matrix from that into Tedana, and then am working on combining the classifications from those two steps and denoising after the fact, which I have a PR open for, but it will need substantial revision before it actually is something we can put into Tedana. So that's it.
I know we don't have a lot of time left, but I just want to throw it out there that I've been using Tedana for aging data sets, and I get a lot of questions about, is it working well? Are the number of components enough? Like we kind of toggled that for a long time, finding that a lot of the default criteria weren't working very well among our older adult samples. And so, if folks want to talk about that at some point, I'd love to talk more about what the data looks like when you do it on subjects that aren't kind of typical in various ways. But yeah, just throwing it out there that if you're also wondering about that, I've had a lot of questions.
Yeah, I was wondering, like, in aging old versus young, the echo times and the T2 decay or whatever, like, is there any study looking at different age groups and looking at the slopes of these components? I don't know. That's an interesting question you are raising here.
I'll mention that I don't think I see her here, but Julie Mosier, who is at I think Mosier is correct pronunciation, at Minnesota, has been using multi-echo data in infants, which have a very different T2. And as of now, they've been publishing with just the weighted average, but I've done some preliminary work on using the denoising, and it seems to work. There's a lot, I mean, that's a really atypical challenging data set, so I don't want to, overstate claims based on one or two data sets I've looked at, but if people are interested, that's another contact. And maybe we can get her to speak at a future meeting here. I'll also mention we're at the hour. I and maybe some others here are welcome to hang out here longer. And I'm definitely interested in hearing on, what people want for future sections, if you're interested in helping or organizing or anything, or just attending. But if anyone, has to leave the hour, it's fully understood, but you are welcome to stay and continue the discussion a bit longer.
Thank you for organizing. It was very useful. And thanks for the speakers. Everything was so good. Thanks. Bye.
Hi, everyone. Thank you for joining.
I guess some are staying a little bit longer I'm Ali. I'm a
Hello.
PhD student at McGill University, working with the multi-echo data from the cohort of cognitive unimpaired individuals who are elderly. And I have had some issues regarding the components that have been extracted from the from tedana on the data, and I've been posted some of the examples during the past few days on the Neurostars, and Dan and Taylor have been super helpful. I was super interested about the decision tree implementation and how like modifications of it could be helpful regarding my question in whether it would enhance the variance explained by the components that are extracted, or it will kind of remove the noise in a way that could enhance the output of the component, I say denoising. And yes, if there is a possibility that they can have access to the PowerPoints of the first presentation, it would be fantastic. And if there is further suggestions you might have, I can include in my approaches to tackle this issue. I am still like incorporating Dan's comment, so I will investigate those as well. But if you have further updates on how we would be able to incorporate those, would be fantastic. And also access the PowerPoint of the presentation at the early meeting.
I think we can share the PowerPoints with the recording.
That would be
I would say
fantastic.
we will send another newsletter with the link to the recording, and we can probably add the slides as well. Yeah.
Perfect. Thank you.
I'll also say on the decision trees, the original decision tree was designed sort of piecemeal, and it has a lot. It seems to work extremely well in a lot of data, but it also has an immense number of arbitrary decisions. That you're doing something a little bit different. Things might work. I added the minimal, which is sort of a little bit more concise, but also has arbitrary decisions. The core thing I think a lot of that I think is worth discussing is that I don't, the method is never going to be perfect, but one of the core questions is, do you have a data set where you want to be aggressive and remove everything possibly considered noise? Or do you want to have a data set that says, I'm going to definitively remove noise, but I want to be extra cautious and never remove something important? So if you're sort of on that side of like, I see removing things I care about, I want to make sure that doesn't happen, it's relatively easy to just tweak some of the thresholds and say, let's just make everything a little bit more forgiving. And if you want to be more aggressive and then say like, maybe you want to be aggressive and then you want to inspect. So you want to, more aggressively remove, and then you're going to remove some things you care about, but then you're going to look at it and try and flag those in some way or another. That's an option. I was actually speaking to Echo that maybe there's a way to sort of flag the borderline cases so we can both be aggressive and then have a step where a human can come in and say, make sure to look at these 5 components to see if you like what we did. It's, ideally it's going to be perfect every time, but frankly, I don't think ICA components are, a perfect way to parse our signal into bold and not bold. So we're always going to have some sort of stuff in a gray area. As long as we're using ICA, which is, something else we're talking about, like, what we can replace it with, are there better, data separation tools? But that's where things are now. And I think the real big step is, now that this is so easy to run and share, as we get more data, if we have an aging population or these other populations or things, and everyone's like, hey, this parameter is bad, we can change it. It's not everyone for themselves. It's like, let's as a community work together to sort of figure out what actually is robust and stable across a wide range of data. And we couldn't ask that question three years ago because we didn't have the tools to actually tweak things and change things and do that stuff. Now that we have the tools, it's possible to sort of say, how do we do this better?
Yeah, sounds good. Thank you so much.
So of the people still here, how often do you think we should do this? I might send a survey out later, but I think bandwidth wise, we're not going to do this more than once, maybe slightly more than once a quarter we can get away with, but not that much more. But that also depends on organizers. If the few of us who organize this are organizing everyone, it's once a quarter. If we have a bigger team of organizers and speakers, we actually could do something once every month or two. But what do people think would be useful in general?
Once a quarter sounds like a pretty good start to me. I've found like, I learned a tremendous amount today, I would say, and I think I'm really impressed by like how many people we were able to bring into this room, how many people you were able to bring in, and like all of the people who are actually such big stakeholders in all the different processing pipelines. I think beyond even just like multi-echo, this is going to be like a really great place for kind of conversation about pipelines. So it's a fantastic initiative. But yeah, I'm happy with once a quarter personally.
Also noticing we're down to kind of more of the speakers here, but of the people who have been quiet, we sort of packed 3 talks in here and had limited time for sort of just the open Q&A. Should we keep focusing on talks? Should we have some of these more open? Do people have strong opinions?
I thought it was really well done, well balanced, because you want to have at least some focus on the call and then leave it up to the public. So thank you guys for organizing this. I'll probably try to speak with Daneko since he's really close by. I work with Signe Bray. You probably talked to her recently. We're working on a young cohort of developmental scans. So yeah, we're trying to get a population from 0 to 18 years old kids all across Canada. So we're gonna actually try to use we're following Tezalo's development on fMRI post tedana as well. Might be able to contribute there as well, since we're going to be using fMRI prep and also tedana. So we're also working in that connection between making fMRI work seamlessly as an input for tedana workflow. So yeah, it's very exciting stuff.
Good to see you, Milton. We can definitely have a chat.
Yeah, I'll try to pop by the office one of these days. You're still working with Nils, right?
Yep.
All right.
I'm going to stop the recording now.